Custom underglow lighting. Why on earth would you even want to do that when there are plenty of perfectly good solutions out there that you can just go and buy? And I already have underglow on my 350Z. But whether it's the cheap Chinese kits or the expensive custom solutions that you can buy, none of them offer the functionality that I want to integrate into my 350Z. And that functionality includes having a display that sits in my dashboard that I can touch and then choose another color, likely from a color wheel, and then have that immediately set. Plus, I want to have some feedback on the interior of the cabin as to what color my underglow currently is, because at the moment, in order to see, I have to open a door and reach and put my hand underneath and see what color my hand is glowing. It's not ideal. So what we're going to be doing in this little series is taking a cheap Chinese kit and then completely updating it with a ESP32 board to control everything, linking that with a display controller that I can put inside of my cabin, and then building a custom PCB to bring everything together. I've actually partnered with PCBWay for this series of videos, and they will be providing all of the circuitry and components and boards and everything for it. So thanks very much to PCBWay for reaching out about that. This is going to be very much a beginner level tutorial. So we're going to get down right into the nitty-gritty of both the hardware and the software, and I'll explain along the way why we're making the decisions that we are. So even if you've got no experience of coding for Arduino or with C++, you should be able to follow it along. So let's take a quick look at the hardware that we're going to be using. When it comes to the actual LEDs themselves, like I said, there are two options. There are the eBay Chinese versions, and there are the more expensive kind of custom versions. I've used both, and to be honest, the actual LEDs themselves, the strip, there's almost nothing between them. They're basically the same thing. The thing that the expensive ones do better is their housing and their surrounding is generally a bit tougher and a bit more waterproof. And the software sometimes is a little bit better from a user experience perspective. Though, to be honest, there's not really a lot of difference between them. So for this video, I've opted to go for the eBay version. These cost me £37. And the reason that I went for them is that instead of being one long continuous strip, you get these 6 segments of lights which are separated with these connectors, which means if you get a section that gets damaged, like I've damaged mine by bottoming out and the one on the side skirt broke because I hit and snapped a light. Instead of having to then replace everything or cut out that section and awkwardly resolder wires underneath your car, you can just unplug the section, replace that one bit, and you're good to go again. So these lights have this standard control module, and when you break it open, you'll see it's dead simple. There's a couple of components on the board and the wires which connect here to ground, data, and a 12-volt positive. It's unusual that the black and yellow wires are opposite on the wiring that you would expect, but that's just a note for later when we actually come to wire this up, that we know that black is data and yellow is ground. We're not going to need this module, so we can just cut it off. And we're going to replace that with this ESP32 dev board. This one is a WRoom32D, and it'd be great for simulating our final product. It's not what we're going to actually use in the end, but it's great to do the prototyping. One challenge that we're going to have with this build is split voltages. The LEDs require 12 volts to run, whereas the ESP32 needs 3.3 volts. Fortunately, we can do that really easily with some level switching when we design the PCB. But for now, we're going to use this 12-volt step-down modulator that runs from my mains just to a standard plug input and then can be split to 12 volts, 5 volts, or 3.3 volts. If we have a closer look at the board, we'll see one of the pains with the ESP32 dev board is that it's super wide. It doesn't fit on a standard single breadboard, but fortunately, all the pins that we need are on one side of the board. When we look closely, we can see we have this 3.3 volt input at one end. We've got all the numbered pins, which are digital inputs and outputs used for controlling things like talking to displays or buttons, and then a ground pin, and that should do us for now. So due to the aforementioned split voltage concern, for now, we're going to run 3.3 volts on this top track and 12 volts on the bottom. It just means we don't risk overloading our board or underpowering the LEDs. When you use these prototyping breadboards, you'll use these jumper wires to connect up the pinholes. And the first thing we're going to connect up is the board power. So we go from any one of the pins in the row underneath the 3.3 volt pin, and then we connect that to the positive track at the top of the board. Then we'll connect up the ground pin in the same way, take any of the ones on that row and connect it to the negative or the ground track on the top of the board. We're going to just run with one half of the strips. They actually run two sets of the lights in parallel, but we'll worry about that later. So now we'll just strip the wires. So again, we'll connect the red positive wire to the positive 12 volt track at the bottom of the board. Then we'll connect the ground, the yellow wire, to the ground track. And the black, which runs data, we're just going to put into any random pin in the middle of the board, just because I don't want to overstretch it to get it right next to the ESP32. And then we can use another jumper cable to bridge from another pin on that row to one of the digital input-output pins in the ESP32. We're going to go for 27 because it happens to be my lucky number. And now with that wired up, we can get the power to the board from this step-down module using some DuPont cables. So we extend the positive and the ground from the 3.3 volt circuit and connect that into the top track. And then we do the same and connect the 12 volt positive and ground to the lower track. If you ever watched any of my previous videos about working with NeoPixels, or you've just got some experience of it before, you'll know one of the things about them is you can't just send it power and have the lights turn on. You need to send it power and data. It needs both of those things in order to work. But sometimes strips have got a little quirk in them. And I can see just by looking at it, this one is going to be one of those examples. Because when we plug in this here, I'm going to just plug in some of the strip. We would expect under normal conditions that when we press the power button, nothing happens. But in this one, it lights up white. Why? It's because these aren't NeoPixels. These are a light strip utilizing the WS2811 protocol, which means that the IC, the integrated circuit that you used to control the lights, isn't built into each one of the pixels. It's separate, and we can see it on the strip. We'll take a look in a second. And also that these things, their default state isn't off like a NeoPixel is. Their default state is white, which is what we're looking at here. So this is, I'd say, a mid-white, probably around 100, 100, 100 in RGB. There's also a second quirk, which is, in fact, if we turn this off and we take a look, we can see that this strip, there's a break every third LED. So 1, 2, 3 LEDs are in between each break. And each section, each 3-light section, has this. This is the WS2811 IC. So that will then regulate the signal for those 3 LEDs rather than just one at a time, which is going to mean when we come to writing the program, if we write some code to say turn on 2 LEDs, it's actually going to turn on 6 because it's going to do them in groups of 3. It's actually beneficial for us when we're doing predominantly static colors because there's going to be a lot of LEDs and it keeps our memory usage down because we're not actually using as many LEDs, but it does mean we have a little bit less finite control. So let's get this Arduino connected up and start writing some code, I guess. Geek mode time. Obviously, in order to do this, we just need to connect the Arduino to the computer. So I'm just going to do that with this micro type B. So with all that started up, let's get a new sketch going, which we've got here. So this is what you get if in a blank Arduino IDE. We're using version 2.3.3, as we can see here. So if I go into tools here, you probably won't have this much stuff, but the important ones are the board here. So you want to make sure you're on the correct one. We're using an ESP32 dev module. which I have in the ESP32 extension. You will need that. If you want the link, it'll be in the description below. So you'll need to have the ESP32 extension in, and then you can use the ESP32 dev module. Port, so here we've got different serial ports. If I unplug the ESP32 and then go back to ports, we'll see only 5 and 6 are available. And when I plug it back in and go back to it, 3 becomes available, which means 3 is the one that I'm now plugging into. So that's the one that we want to use for this. And we can test before we do anything else that we're correctly connected by just verifying this sketch, which it will verify really easily because there's no code in it. We're going to try uploading that to the board by clicking the upload button. And then once it gets to connecting down here in the input, we press and hold the boot button on the ESP32 until there it starts uploading. Once it starts uploading, we know that it's actually connected and able to upload code correctly to the board. So what we're going to do initially is just get the lights to change to a different color so we can verify the correct color profile that we're using for these LEDs and just make sure that we have the control of them that we want. We're going to start with a brand new blank slate sketch file, and we need to include the code for NeoPixels. It's created by a company called Adafruit, and you can go and download the library, which gives you all of the functions and the code for NeoPixels. Now, I've already got that installed, so I've got quick access here to add it. Just go to Include Library, and I've got it at the top here, Adafruit NeoPixel. Clicking on that will include the Adafruit NeoPixel.h, and the .h is just a handle for the library. The H means header. Well, you can refer to the official documentation, which is available here. I'll put this link again in the description. And as you can see at the top, we've got the include file, which we've just put at the top of our sketch file. And then we've got these public member functions. These are all of the functions that you can access in that library that allow you to do things. And we're going to be using some of these. And what this documentation does is show you the format in which you can access these things. For example, set pin here. If we were going to be using this set pin function to change the pin output number, you change it to an int 16. So that's basically a integer value. It's just going to be a number, and that's going to set P, which for this function is pin. The one we want to use to start with is this very first one. It's the constructor, which tells our sketch file that we're going to be doing something with the NeoPixel. So we just want to copy that and put it into here. This might look a little confusing if you're not used to seeing this format, but it's actually pretty simple. What it's telling us is these are the things that the Adafruit NeoPixel function requires in order to know how to work. So N is the number of LEDs that are available. And all of that is available here. And so when length, pin, and pixel type are known. So N is the number of pixels or LEDs. So in this instance, we're just going to use 2 for now, because really we just want to see if 2 LEDs light up, or if, as suspected, 6 light up. The pin number that we've used to connect the data line, which is 27, and the NeoPixel type. So this is assuming we're using standard NeoPixel LEDs, which go in the format GRB, green, red, blue. There's a chance these ones send those colors in a different order. So we might need to change this, but we'll come back to that as and when. Then we need to give this a name by which we will refer to it throughout the rest of the code. So when we want to do something like send colors to it or something, we need to give it a name that we can use. So we just use LED. So then if we want to show the LEDs, we can use LED.show or whatever it might be. We also need a semicolon at the end. There's a big no-no we've done here, which is just putting these numbers directly into the function. You can do it and it will work, but it's not very readable and it doesn't allow you to change things particularly easily. So what we're going to do is create a couple of constants that we can then refer to throughout the code if we need to. In coding a lot, you'll hear about constants and variables. Constants are things that you set once and they are just referred to as something else, whereas variables are things that can change. For example, the pin number that we're going to be using as our data line isn't going to change, but the color is. So you would have the pin number as a constant, and later on we'll have the color as a variable. But that'll make sense as we get into it. To set up some constants, we use #define, which is just a keyword to say we're going to define something. Then we want to define what number of LEDs that we want to light up. So we'll call this num of LEDs and then do 2. Now, when you're creating constants, it's generally standard practice to do them uppercase like this with underscores in between the words. It's called snake case. It just makes picking out constants throughout your code really easily. And then we'll do another one. Define the pin for the LEDs. And we'll do that as 27. Then what we can do is just take these constants and replace them in this call function. The reason we kind of done that is later on, for example, we might have some loops down here that need to know how many pins it wants to change. So instead of using just defined numbers in there, and then if that number changes, we have to change all those numbers. So we can refer to num of LEDs later in the code. And if we ever want to change that number, we just change it once at the top of the code rather than having to go all the way through it. So with this setup, we can just verify just to make sure we've got no problems at this point. I don't think there should be any. There's very little that has happened so far. Good. So that all compiles. So setup and loop here, what is the difference? Roughly speaking, setup runs once when the code starts. So when your Arduino or your ESP32 boots up for the first time, it runs setup once, then it enters into loop, and loop runs forever. So setup is exactly what it sounds like. It's the code that done once at startup. Loop is the code that continues to execute for the lifetime of the Arduino being on. Generally speaking, setup is used to initialize things. And in this case, it's going to be no different. A common one is going to be serial. So we have serial, and you can see it gives me a load of different things. Begin is what we're going to use with the baud rate of 115/200, which is just the one I like to use. This just allows us to print things to, if we go to tools and then serial monitor, it'll be serial here. And then if we wanted to print out things like what is the current color or what is the current, what is the state of variables, we'll print them into here, which means we can just keep an eye on how the code is executing. So you'll generally have a serial.begin at the start of your code because serial and print is a thing that you will use a lot. Then we'll set up the kinds of pins that we're going to be using. So whether they're input pins or output pins. And we do that with some Arduino code, which is pin mode. And we want to refer to the pin that we're outputting, so the pin for the LEDs. Again, this is a good reason to use it as a constant. And we're going to say that one is going to be an output. So this can be either an output, an input, or a special one, input pull-up, which is one that we are going to be using. We'll worry about that when we get to it. And then we need to tell the lights, we're going to start. We've got code we're going to send you. We want to operate on you. So we use our special LED code that we defined here at the top and just tell it begin. And again, once you put the dot in, it will show you all of the things that are available within that library just to make life a lot easier. So led.begin. At this point, our kind of like real base code is set up and we want to do a test to see if this RGB format is correct. So we're going to do that by sending it an RGB color and see what color it actually lights up. So we're going to send it what we think to be red, because I like to work in RGB, red, green, blue, in that order. So if we send it what we want to be red and see if it lights up red, that means red is correct. There is a piece of code that will allow you to fill the entire strip of lights with a single color, but I don't want to use that. I don't like using that one. So what we're going to do is the one that allows us to set each individual pixel, which is led.setPixelColor. And then there's a few different things you can do here. The first one is, let's just put the letter N in there, which means number, or the LED number. So like LED1, I want to make LED1 a certain color. And that color is going to be a combination of red, green, and blue. So in this test, let's just start by setting the first pixel, so LED number 0, and we'll give it a value for red, so of 100. Numbers for colors go between 0, off, and 255, maximum brightness. So we'll do 100 for red, 0 for green, and 0 for blue. So this should just boot up and say, okay, set that pixel color in memory. It's not actually setting it on the strip, it's just setting it in memory. Then once that pixel color has been set, we need to led.show. And then that will take whatever new values are stored in memory and send them out to the strip. What this should be doing is testing whether or not the first one in the format is red. So if this comes on red, that's great. If it's blue, then that means this GRB format is wrong here at the top. So we're going to just verify it to make sure it works. Go to the output, upload that, press and hold the button to make sure that it uploads correctly. There we go, it's up. So when I turn this on, what do we have? Okay, so we can see we have two things here. We have the first one is red, and then these three are off because they've been sent nothing. And then the rest are white because they haven't had any information been sent to them yet. So that's interesting. So it's defined these pixels. So I reckon if I do this to 3 and then upload that, the next combination should go off because they're not actually being sent anything. I've got a feeling in order for this to execute, I'm going to have to turn it off and on, but oh no, okay. Okay, so there, the next set have gone off. But that is red, so that's good. So R is correct. Now let's try green. So pixel 0, red, green, blue. Upload green. Okay, that's gone blue. So it's RBG, red, blue, green, which probably means I need to just switch blue and green in this format at the top here. So if we go to BRG and then we upload that again, this should hopefully now be green. Yeah, great, green. And just to verify, if I turn the green off and turn the blue on, just check that. Let it upload. It's blue. And we can just do one last verification by using 3 of these, dead simple for now. So pin 1, pin 2, and we'll do, the first one is red, the second one is green, and the third one is blue. Red. Just upload that. Red, green, blue. As expected, red, green, blue. So by changing this Neo BRG format here, basically just changes the order in which it expects the code. So I can always write in RGB, even if the lights themselves don't expect RGB. And also, as we suspected, these are in triplets. So I'm just controlling 3 LEDs, and I'm actually controlling 9 LEDs because these are impacts of 3, which is good because it means the actual LED strips, I'm not sure exactly how many lights are on there, but it's probably a couple of hundred, which means that the memory allocation for the package could be quite large, trying to control hundreds of LEDs. But the fact I can divide that number by 3 means it's a lot more manageable. Now, how will I do all of these at once? First off, how many are on this full strip? So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36. So there's 36 on this strip. So the actual number of LEDs is 36 divided by 3, which is 12. 12 LEDs down this side. And I don't want to have to individually allocate all of these here. So what we'll do is we'll create a function. And a function is a reusable piece of code that you can access anywhere in your code. Just makes things a little easier and a little bit readable. Now, functions in C++ for Arduino have to have something that they return. And sometimes the thing that it returns is nothing. So we just use a void. Basically just saying execute, and when it's executed, done. It doesn't need to return, oh, this has happened or this hasn't happened. You can do, but we're not going to do it in this instance. What we'll do for this function is do set LED strip. And then we want to set the strip to red, green, and blue, which are going to be values that we pass into this function, which will make sense in a minute if you've never written a function before. So I want to run through all of the LEDs and set all of the LEDs into memory before I send that value to the full strip. And we do that using a loop. What a loop does is continue running until the parameters that you've defined within it are completed. So it's usually like between two values. So count 0, 1, 2, 3, 4, 5, 6, 7 until you reach 20. And when you reach 20, stop counting, for example. So we're going to use a for loop. So we write that as for, and then it needs to take the value that we start from, the value that we end at, and how often we increment. So usually you'll start at 0 for something like this for lights, because we're going from pin 0, and then it'll go until the max number of LEDs that we have, and it'll increment one at a time. But we don't quite write it like this. We use a variable in here which increments with each loop, because what we need to do is inside this for loop, we need to do this set pixel color here, and we're going to set the pixel for the variable that we have defined in this loop. What we'll set here is the LED number. So we want this to start at LED number 0. So our start point here, we're going to say that the number is an integer. So we'll just call it an integer. LED number is equal to 0. So we're going to go from where LED is equal to 0, and by putting int at the start here defines what LED number is. We only need to do it in the first instance. And then we can go until LED number goes up to the maximum number of LEDs. So here it's the number of LEDs. So it's while it's less than the number of LEDs, and it's less than because of the fact that it uses 0 as the first LED. So the first LED isn't 1, it's 0. So by the time we get to 12 in this loop, 12 will be the next one after the end. So we go until the one before that. So it's basically an array, and it starts at 0 as opposed to starting at 1. So we use less than. And then each time this runs, we want to have the LED number increase by 1. And there's a shorthand for that, which is ++. So what this is saying is start this loop, start with LED number being defined as 0, and continue looping until we hit this parameter, which is the number of LEDs, and each time we loop, increment by 1. And then as we go through this loop, the LED number, which we set in it, is available here. So the first time this loops, this LED number will be 0, then it'll be setting pin 0 to red, then it'll be setting pin 1 to red, pin 2 to red, pin 3 to red, and it'll keep going until it hits the very last one. But we've seen here that we can have red, green, and blue, which are things we want to send this LED strip. So we need to define what these are. So these are going to be ints because, again, they're just integer numbers. We could do unsigned integers at this point to define their length, but it's really overcomplication for something that we're trying to do quite simply. So these are integers, and instead of just having this hard defined here, we'll put red, green, and blue. And then after this, we need that led.show. So it's going to execute all of these, set all of the values, and then update them to the LEDs at once, rather than doing it after each individual LED. You can do it after each LED, but it's memory inefficient and it's speed inefficient. You're best to just set them all once and then send everything in one go. So in this loop, instead of doing any of this, we just use this set LED strip and then pass it the red, green, and blue values that we want. So if we want red, we can just set LED strip to that value. There's a common issue that you get with a thing called debouncing in Arduino, which is as and when we start to put inputs into this thing with the display that we're going to build, you want to make sure you can't do too many things too quickly. So we'll just add a delay here of 100 milliseconds, which basically means it'll send the code out, then wait 100 milliseconds, and send it out again, and then wait 100 milliseconds. Really, we'd want to put a state manager in here, and we will do that at some point. But for now, again, this is the entry-level basic bit of code for this and testing and getting these lights working with an Arduino. This will be fine. So if we just verify that code. Oh, there's an error. Oh, yes. This is supposed to be semicolons here, not commas. And then we'll upload that to our Arduino. So when we switch this on now, hopefully we're all red. And red. So everything's red. For now, I'm going to stop this video here at this part of the progress. We've shown that we can connect an ESP32 Arduino to some budget Underglow lights that you get from eBay and actually control them and do the things that we want to do with them. In the second part of this video series, we're going to be using a kind of 2-inch round screen microcontroller and building a custom user interface into it, which we could then use to operate and change these lights. There's no point me going too far down the rabbit hole at this point in time until we start working on that, because we need to use specific libraries. We're going to be using LVGL, the Light and Versatile Graphics Library, which is a really good little tool for weird displays like watches that we can then use to control these lights. That's going to be quite a long and niche self-contained video. This is more an introduction to actually connecting these lights to an ESP32 board and a look at what we're going to be doing next. The next parts, I think, is where things are going to get really kind of interesting with this little build. Hopefully this video has shown you that if you are looking at building custom Underglow or any lighting system for your car, you don't have to go out and buy the really expensive NeoPixel strips. You can do it and get full control with these cheaper lighting options. And that if you do decide to do it this way, this has shown you that there are a couple of quirks and things that you need to consider, such as the triple light issue. Like I said, this channel is now going to be completely dedicated to these kind of builds, Arduino projects, cool displays, lighting, sound stuff, cool electronic stuff, predominantly for your car, but you know, they'll have other uses that you can do elsewhere. But that's what we're going to be doing here now. We're no longer Valentine Autos, we're now Garage Tinkering. And if you want to see the cool car stuff that I'm working on and how some of these things actually get used and put into cars, Valentine Autos is still available. It'll be linked down below. So the car stuff is now going on over on a different channel. So if you do want to see more of this stuff and get into some very simple, but also some very, very, very niche and very complex Arduino code and learn how to do it all in the process, make sure you subscribe, because we've got lots and lots and lots and lots coming. Anyway, whatever you do with the rest of your day, folks, have a wicked one. I'll see you in the next video. Take it easy, peeps. Bye-bye.